So let's optimize by finding the minimal surface area of a can of volume 20 centimeters. And the first thing we need to do is find out, well, what is the surface area of a can? We have the top circular piece, a bottom circular piece, and we have this height. And I believe, so the top piece is going to have area pi r squared. The bottom piece is also going to have area pi r squared. And then this vertical piece is just length times height, and the height is h, but the length is the circumference of the can, which is 2 pi r. So altogether, it means that the area of this can, the surface area, is going to be equal to 2 pi r squared plus 2 pi r h. But we have a constraint, don't we? So this is our surface area. We're constrained by the fact that we want the volume of the can to be exactly equal to 20 centimeters. Yeah, because this is the vertical piece. So we have this added information. What is the volume of a sphere? The volume of this cylinder, is going to be the height times the area of the base. Height times, what's the area of the base is pi r squared. And we're fixing that exactly equal to 20 cubic centimeters. And with this, we want to minimize the surface area. We have our auxiliary equation here that relates our volume to our radius. And maybe before I go further, now I'll take the derivative. To minimize surface area. And I'm going to do it using implicit differentiation, in part as a review of implicit differentiation, and I'm going to take my derivative with respect to r. So I'm going to take the derivative of this side with respect to the radius, and then I'm going to take my derivative of each of the terms on the other side with respect to radius. Well, maybe this isn't exactly how you wanted to solve the problem, but I think it's a cool way to solve the problem. All right, the problem is that here in this piece, I have some h's in here, and I don't want to have multiple variables, right? So I'm going to, instead of having my h in here, I'm going to solve for h using my auxiliary equation. This equation can be rewritten so I get h is equal to 20 divided by pi r squared, which is the same thing as 20 over pi times r to the negative 2. So including that in my equation, I'm not taking the derivative yet. I'm just going to plug in that value. I was going to do implicit differentiation, and then I realized that's probably not something that you want to see, because we'll have to use product rule and it'll end up getting pretty messy. I'm solving for h and rewriting that as 20 divided by pi times r to the negative 2. And this final term simplifies quite a bit. I see that my final term r squared dr. The pi's cancel each other, one of the r's cancels each other, and the 20 times 2 becomes 40. So I end up with 40 r to the negative 1 dr. Now that I've used the auxiliary equation, hooray! Let's do the hard work of calculus. So the derivative, we're going to take this derivative and set it equal to 0. So 0 is going to be equal to the derivative of this, which is 2 pi, because r is squared, the derivative of that becomes 2r, plus the derivative on this side is going to be 40 r to the negative 1 Recall that that means that by power rule, we get negative 40r to the negative 2. Let's simplify this slightly. I get 40r to the negative 2 by adding 40r to the negative 2 to each side, 4 pi r. Now I'm going to divide both sides by 4, and I get 10 over r squared equals pi r. And moving these pieces around, I'm going to multiply both sides by r squared and divide by pi. And I got 10 divided by pi is equal to r cubed, which means that our radius value is the cube root of 10 divided by pi. Now that I have the radius value, I can go back to our auxiliary equation. Recall that h was equal to 20 divided by pi r squared. Plugging in this value, it ends up being pretty messy. That means our h value is going to be a function of pi, 10 divided by pi, all to the 2/3. And if I wanted to put this into a calculator, I could come up with an exact, or a decimal approximation. I'm going to leave this as the messy exact value, leaving this radical in the denominator because I don't care about radicals in the denominator. So looking back on this problem, what did we do for this optimization? 1, we came up with an equation for surface area that we were going to minimize. 2, we came up with a second equation that relates h and r, our two variables, so that we could solve one of them. And we plugged in that solved variable into our surface area equation, took the derivative, set it equal to 0, and solved for each of our variables.